Hi everyone, I hope you're having a good Wednesday. Welcome to the live stream. So tonight we are going to be continuing our work with acids and bases. We are going to get quite heavy into the math here because we are going to work, hopefully if I can get through them, hopefully we're going to work two different titration problems and their multi-step titration problems. But the first thing I want to do is, of course, I want to get some definitions going before we actually jump into those titration problems. And let's go ahead and jump in. Okay, here we go. So the first thing that I want to do is I want to talk about the difference between strong and weak acids and bases, because many people get this confused with concentration or what the pH is of the solution. But it actually has to do with how it acts in aqueous solutions. So for your strong acids and your strong bases, they are going to completely dissociate or completely ionize in aqueous solution. Now, for all of these problems here, we're always going to be in aqueous solution. For weak acids and bases, they are only going to partially dissociate or partially ionize in aqueous solution. Now, I did list here just kind of your common strong acids and your common strong bases. But let me write out some equations and explain hopefully a little more clearly what I mean by completely dissociate versus partially dissociate. So let's take our common strong acid. We'll just start with the first one, that's hydrochloric acid. And when we put that in water, what happens is we form the hydronium ion. Because it's an acid, it's going to donate a proton to the water. And we get chloride anions. Now, there are a couple of things I want to point out. First of all, this arrow only points to the right. So what this means is this reaction goes to completion. So once you have dissolved the hydrochloric acid, there is no more hydrogen bonded to chlorine in the solution. They are no longer together. All of those hydrogens are now associated with a water molecule, i.e. the hydronium ion, and you've got the chloride anion. So this is a strong acid, and you only have the forward reaction. Okay, as opposed to a weak acid, let's do hydrofluoric is actually a weak acid, so HF is a weak acid. When we put it in water, it still acts as an acid. It's still going to donate a proton to water to form a hydronium and the fluoride anion, but you'll notice I have used equilibrium arrows. That means in solution, let me switch over, you have some hydrofluoric acid that are still bonded together, and you have some hydronium and some fluoride. So you have the forward reaction that happens, but you also have the reverse reaction that happens. So again, the hydrofluoric acid partially dissociates or partially ionizes in aqueous solution. And the same is true for the bases. So let's write here. This is a weak acid, and we'll say forward and reverse reactions. Whoops. Okay, so we're getting both the forward and the reverse reactions. Again, the same thing is true with the bases. If you have a common strong base, again, we'll take lithium hydroxide because it's just right there. When we put this in water, it completely dissociates to the lithium and hydroxide cation and anion. There is no more lithium hydroxide in solution. Again, it's only the forward reaction. This is strong, a strong base, as opposed to ammonia, the classic weak base. When we put it in water, again, notice I do the equilibrium arrows. It is going to give you the ammonium anion and the ammonium cation and the hydroxide anion. This is a weak base. Again, we've got the forward and reverse reactions happening, which means you have equilibrium. Okay, So those are our definitions of what it means to be a strong acid or a strong base versus a weak acid and a weak base. Again, it's not tied to what the pH is or what the concentration is. You can have a very strong acid but have a very dilute solution that's got a pH that's not super low, versus you could do a very concentrated solution of a weak acid and get that pH way low. So again, students like to tie it to concentration, but it's not tied to concentration. It's all tied to percent dissociation. Okay, so let's talk a little bit more about these weak acids and these weak bases, because the mathematics here starts to get a little bit complex. So what I want to do is I want to show you how to write Kas and Kbs, again for acids and bases, and then we'll do calculations where we're calculating the pH of a solution of a weak acid and the pH of a solution of a weak base, again before we get into our neutralization reactions. So let's take our, let's do a weak acid. Let's do nitrous acid. Okay, again, it is in equilibrium with the hydronium ion and your nitrite anion. Okay, so we're going to start actually with the KEQ, and then I'll show you when it becomes the Ka. So if you remember writing equilibrium constants, it is the concentration of the products. Okay, so these, I have two products, so hydronium ion and the nitrite anion, over the reactants, which is our nitrous acid and our concentration of water. All right, so this is just the equilibrium constant. We make it a Ka because our concentration of water here isn't going to change, and it changes a minuscule amount. So if you remember, the Kw for water is 1 × 10⁻14th. So mathematically, we can consider the concentration of water to be a constant. So what we do is we move the concentration of water and we fold it into the KEQ. This gives us our Ka. So this is for an acid. It's an equilibrium constant for an acid in aqueous solution. And what it does for us is it just simplifies this expression. So you'll notice I'm no longer writing in my concentration of water because I have folded it into the KEQ, and now we have a Ka. Let's do the same thing for a weak base. You'll see it's very, very similar. And we'll always do our classic weak base because it is the easiest. We'll do ammonia. Again, it is in equilibrium plus hydroxide anion. All right, again, I'm going to start with just the KEQ, which is concentration of products over concentration of reactants. Okay, so concentration of products is our ammonium cation and our hydroxide anion over our reactants, which is ammonia, times our concentration of water. And just like when we made our Ka by taking our concentration of water and folding it into KEQ, we're going to do the same thing here. Again, the concentration of water is not changing. It is considered to be constant, so we can just put that into our other constant in this equation, the equilibrium constant. So in essence, you can also think of this as putting all your constants together and keeping all your variables together. Okay, so now we have a Kb for base, and what it does is it simplifies this expression to our ammonium cation, our hydroxide anion, and the concentration of ammonia. Okay, so hopefully this makes sense in terms of how we get these expressions, these equilibrium expressions, but I think the tricky part is not only knowing how to write it, but then how to apply it. So let's actually do a couple problems where we're going to have to do these equilibrium calculations. Okay, so first problem. If 2.53 grams of nitrous acid is dissolved in 125 milliliters of solution, what is the resulting pH? And the Ka of nitrous acid is 4 × 10⁻⁴. Okay, so we're going to do basically the same thing we just did. So we actually already have our Ka for nitrous acid. So I'm just going to pop back here and show you again our Ka for nitrous acid right here. Notice that these are in brackets, which means we need concentration. So actually the first thing that I'm going to do for this problem is I want to get the concentration of nitrous acid. And right now I have grams and I have volume. So that is my first task, is to convert grams into moles and then make that into molarity or concentration. So taking my grams of nitrous acid and converting that into moles. I did write down that molar mass. Here it is, 47.013. Oops, I forgot my hydrogen, sorry. Grams of nitrous acid over 1 mole of nitrous acid. And this gives me 0.05381 moles of nitrous acid. Now to get concentration or molarity, I'm going to take my moles of my solute, which is nitrous acid, over liters of solution. I have both of these numbers. I just calculated my moles right here. 0.05381, that is moles of nitrous acid. And now I need my liters of solution. So if I go up to my problem, I see that I have 125 milliliters of solution. Of course, this is a very easy conversion. You just want to shift that decimal point 3 places to the left or divide by 1,000. And you get 0.125. This is now liters of solution. And this concentration is 0.431. And again, this is molarity. Let's make sure there are no questions. Okay, so again, I'm doing a lot of math. I'm going to try to keep up with the chat. Please feel free to ask any questions because again, the math can be a little confusing at times. Okay, so now that I have concentration, what I can do is I can start to actually think about the reaction and trying to, again, if I'm trying to find pH, I need the concentration of my hydronium ion, right? Now, when we dealt with strong acids, it was very easy because, again, it's just a forward reaction, but we've got to deal with equilibrium. So what we need to do is we need to set up what a lot of students call either a rice table or an ice table. They're both the same things. I tend to call it a rice table because I always like to include my reaction. So R for rice is the reaction. So we have our nitrous acid plus water in equilibrium with the hydronium cation. And oh, I wrote that as nitric acid. I'm sorry. This is nitrous acid. Nitric acid is a strong acid. And our nitrite anion. Okay, so that's R. Now we're doing I. So again, we're going to do rice, R-I-C-E. I is how much you have initially. Well, we just calculated our initial concentration here. I'm just going to write that in there. We don't worry about water. Remember in Ka, we folded that concentration of water into the KeQ. So it is constant. You can just leave that column blank. For our hydronium and our nitrite, initially we don't have any of that. So you think of this being at the very beginning of the reaction before any forward reaction has happened. So I have 0 of both of these guys. Okay, so that is my initial amount. Now for C is consumed. How much of my nitrous acid is going to participate, you could think of it in that forward reaction to produce products. Because remember, it is a partial dissociation. It's not a full dissociation. Now, I don't know how much it is. So I'm going to call that X. I know that some is going to dissociate, but I'm not sure how much. So I'm going to say minus X because, again, some is going to dissociate, but I don't know how much. However, based on stoichiometry, remember, these are all 1-to-1 ratios, which is fabulous. That means if I'm going to use up X here on the reactant side, I am going to form X amount on the product side for both my hydronium and my nitrite. Now remember, we're after pH, so we're really after this concentration of hydronium ion. Okay, that is my consumed row, but we haven't finished spelling rice yet. We need E, and E stands for equilibrium. So what I'm doing is I'm just adding my rows. So for equilibrium for my nitrous acid is going to be 0.431 minus X. Again, I still don't know what X is, so I'm just putting these columns together. Of course, 0 plus X is just X, and 0 plus X is X. Again, if you want to make it more clear, you can write 0 plus X. It's totally fine. Okay, these are our equilibrium concentrations for nitrous acid, which means, let me just pop back here, I can plug that into this expression right here, because these are our equilibrium concentrations. Yes, we still have X in there. Don't worry, we're gonna get to that. It's all gonna work out. So I'm going to, let me just rewrite my Ka here. Again, this is concentration of hydronium times nitrite over, again, nitrous acid. All right, so I'm just taking these quantities and I'm plugging them into here. So my concentration of hydronium is just X. My concentration of nitrite, again, is just X. And my concentration of nitrous acid is this quantity down here, 0.431 minus X. Okay, so again, I've just taken these equilibrium concentrations and plugged them directly into my Ka. Now, I have a value for Ka because my problem gave me my value for Ka. So I can say this equals 4.0 times 10 to the negative fourth. Okay, so we now have an equation with one variable. We can solve for X. However, it would be great if we could simplify this, right? Because we can solve for X here, we're going to have to use quadratic equation. But if I can avoid using quadratic equation, I want to avoid using quadratic equation. And the way I can avoid it is if I can simplify this quantity down here to just 0.431, if I can drop that minus X, that would be fabulous. So there is a way we can test this. And I'm going to need an extra screen here, aren't I? I totally am. Okay. So this is what I call like my side calculation. So there are two rules that you can use to check and see if you can drop that minus X, if that's going to be okay. Because if X is really, really, really small, then subtracting it doesn't, in essence, change the number enough to change your calculation of pH. So the first rule that I am going to use is I'm going to take my initial concentration of acid divided by my Ka. If that is greater than 500, it means I can drop that minus X. So for my specific problem, I have my initial concentration of my acid is 0.431. 0.431, sorry, that's a decimal, over my Ka for my acid, which is right here. So I'm just going to plug that in, 4.0 times 10 to the negative fourth. Okay, so I want to calculate what this value is. Let's see, I did do that and I got 1074. I want to check and make sure that is greater than 500. Yes, it's greater than 500, which means when I go back to my equation, I can drop this. Now, once we calculate X, I'm going to show you another way that you can double check to make sure that that assumption is correct. So you have two checks to make sure that this assumption is not going to alter your pH too much. Okay, so now my Ka, oh, it simplifies so much, it's fabulous. So now my equation is simply 4.0 times 10 to the negative fourth. My numerator just becomes X squared, and my denominator, because again I dropped that minus X, is just a constant. So now it's so much easier to solve for X, right? Because you're just going to end up doing a square root once you move this constant over. Let's see, I did that calculation. So X is 0.0131. Okay, let's make sure. Yeah, okay, no questions. I kind of got going with the math here. I tend to do that. Let's keep in mind We've solved for X, but let's keep in mind, what is X in the first place? So remember, we defined X as how much is consumed. It is our concentration of hydronium, and it's also our concentration of nitrite. So this equals our concentration of hydronium, and it equals our concentration of nitrite. Now, we're most interested in our concentration of hydronium because we're trying to get to pH. So again, and we'll see this in the next example that we do need to keep in mind what X means, because it's easy to get focused on solving for X and forgetting what X means. I'm going to have to go to my next page, aren't I? Yes. Okay. And sorry, I also want to show you your other check called the 5% rule, just to make sure that your assumption of dropping that minus X is okay. So this one is actually called the 5% rule, and it's a percent dissociation. You are going to take your, oh, sorry, not your concentration. I was getting ready to do my other rule. You're going to take your value of X, which you just calculated, and you're going to put that over your initial concentration of acid times 100%, and this should be less than 5%. If it's more than 5%, your assumption is not valid. All right, so X, we did just find our value for X. There it is, 0.031. So I'm just going to plug that in. 0.00131, sorry. And we have our initial concentration of acid. Actually, I wrote it up here. It's right there. 0.431 multiplied by 100%. Okay, so if you put that in your calculator, you get 3%, which is less than 5%. So yes, our assumption is correct. It's fine that we drop that minus X. It's not going to change our calculation for pH. Speaking of which, let's actually calculate what our pH is. So remember, we're looking for our concentration of hydronium, which we just found because it is X. So this is really easy. Our pH is just negative log of 0.0131, which gives us a pH of 1.88. And that is the pH of this particular concentration of acid. Let's make sure there are no questions. Okay. All right, so let's go on to our next problem. So we just did a weak acid. I want to do a weak base. So I want to calculate pH and if I've got a solution of ammonia. So this one particularly says, of a solution, if 40 grams of ammonia is dissolved in 0.5 liters of solution, and we have the Kb for ammonia. Okay, so we're going to approach this the same way that we approached our weak acid because we're in equilibrium, but we first have to get concentration. So if you remember, hold on, I have to go back a couple spaces here. We did do the Kb for ammonia, and we've got concentrations of everything. So we need to get concentration first. So there's my acid, here's my base. Let's get concentration. So I have 40 grams of ammonia. Let's convert that into moles first. So the molar mass of ammonia, there it is, over 1 mole of ammonia. Okay, so we have 2.349 moles of ammonia. We need concentration. Remember, molarity is going to be moles of, in this case, ammonia over liters of solution. Oh boy, can I squeeze this in here? We just calculated, oh, why did I put a 0 there? We just calculated our moles of ammonia, 349 moles of ammonia. Now we need our liters of solution, so let's go back to our problem. You can see it's dissolved in 0.500 liters, which means our concentration of ammonia is, let me find that calculation, there it is, 4.70. Again, that's concentration, that is molarity. Now that we have concentration, we're going to set up our rice table. Again, R is for reaction. So we have ammonia in water, and it is going to form the ammonium cation and the hydroxide anion. Okay, that's R. I is initial. How much do we have initially? We just calculated the concentration of ammonia that we have initially, and that is 4.70. Remember, don't worry about water. You can assume its concentration stays constant through this whole process. And we don't have any ammonium or hydroxide initially. Okay, so that's RIC is consumed. So we know that some of the ammonia is going to participate in the forward reaction. Some of that ammonia is going to go on to form ammonium and hydroxide, but we don't know how much. This is why we call it X. So I know some amount is going to be used up. Now, whatever is used up is again formed over here because we have a 1-to-1 stoichiometric ratio across the board here, which again makes our calculations a lot easier. So RICE is equilibrium, which means I am just going to add down the columns. So equilibrium for ammonia is 4.7 minus X. Equilibrium for ammonium cation is again 0 plus X. I'm just going to write X, and I'm going to write X for hydroxide here. All right, hopefully you're seeing a pattern that this is very similar to the problem that we just did. Now we want to use our equilibrium expression. And we already know this for ammonia because we wrote it down. So this, whoops, I meant to do ammonium, not ammonia. NH4 times hydroxide over ammonia, or NH3. Okay, so again, I am just going to take the concentrations from my table, even though they have X in them, and just plug them into this expression. So my concentration of ammonium is just X. My concentration for hydroxide, again, is also just X. And my concentration for ammonia is this expression over here. So I'm going to put this in right here, minus X. Okay, we need to solve for X, but we need one more thing. We need the value of Kb. Well, the problem gave us our value of Kb. So this is 1.8 times 10 to the negative fifth. Again, I just got this from right here. The problem gave it to me. If the problem doesn't give you a Ka or a Kb, then often you need to go look it up. And so the back of your textbook is a great place to look this up. Or if you're in like a testing situations, a lot of times they give you tables of physical constants and you can find it there. Okay, so now we have an equation. We have one variable. We can solve for X, but I'd really rather not use quadratic. So let's test and see if we can drop this minus X and make our calculation a lot simpler. And of course, I'm going to need an extra page. Okay, so first we're going to, let me switch over to green here. We're going to use our rule where we're going to take, we're not dealing with an acid. We're dealing with a base. Our initial concentration of base over our Kb, this should be greater than 500. So for our specific problem, our initial concentration of base, which is our initial concentration of ammonia, is 4.7, and our Kb is 1.8 times 10 to the negative fifth. So I'm just going to plug that in. So this is 4.7. and over 1.8 times 10 to the negative fifth. Okay, so I'm just going to pop that in my calculator, see what I get, and I get 2.6 times 10 to the fifth. That is definitely greater than 500. So because that number is so much greater than 500, I'm feeling really good about this assumption. All right, so that means this expression is going to simplify. I can drop this minus X. So let me just switch out here. Okay, so I am coming on up to this space right here. So I still have my Kb, my 1.8 times 10 to the negative fifth. And maybe I'll just delineate that a little bit. My numerator here simplifies to X squared. And my denominator, again, I have dropped that minus x because I checked my assumption. And of course, I'll check it again once I solve for x. So my denominator simply becomes 4.7. Now this is easy to solve because I just need to move the 4.7 over and take the square root. Super easy. So x equals, give me a second, let me find where that went. 9.20 times 10 to the negative third. Okay, that is our value for x. Let's go ahead and check our assumption, and then we'll come back and we'll talk about, again, have to remember what x means and all of that good stuff. So let's check our assumption. This is our 5% rule. 5% rule. So I'm going to take my value of x over my initial concentration of base times 100%, and this should be less than 5%. Okay, so x was 9.2 times 10 to the negative third. So let me pop that into the numerator. And my initial concentration of base, you can see, is 4.7. I'm going to multiply by 100%. Okay, so when I put that in my calculator, I get 0.2%, which is definitely less than 5%. Again, it's a good bit less than 5%, so there is my check mark to say, yes, for both of my tests, my assumption is fine, it's correct, it's not going to change what my pH actually is. Okay, now let's talk about what x means in the context of the problem. So what is x? So for us, x is our concentration of ammonium and our concentration of hydroxide. What I'm most interested in is my concentration of hydroxide. Now remember, pH is equal to negative log of hydronium. I don't have hydronium yet, so there are a couple different ways to go about this. What I like to do is I like to go ahead and take my concentration of hydroxide and calculate my pOH and use that to calculate my pH. But you can also take your concentration of hydroxide and then calculate your concentration of hydronium, and that will give you your not your concentration of pH, that will give you your pH. So again, there are different ways to do this. Choose the way that makes the most sense to you. So I'm first calculating my pOH. This is simply negative log of my concentration of hydroxide, which I know for this problem because I just calculated it. 9.2 times 10, I'm just going to have to squeeze a little bit there. So my pOH here is 2.04. To get pH, I'm just going to do 14 minus 2.04. This gives me a pH of 11.96. Okay, so I do want to point something out. If you had just forgotten, again, what your x means, or sometimes when you're going with these problems, you kind of just keep chugging and you forget to double check with your problem and what's going on. So let's say you didn't realize you're calculating pOH. You just took the negative log of this and you said, no, this is the pH. Well, that would give you a pH of 2.4. That would be an acidic solution. So what I want this to do is I want that to kind of raise some red flags, and I would want you to say, wait, a pH of 2 for a base? That doesn't make sense. Bases have pHs that are above 7. So I should be above 7, and if I have a pH of 2, that means I'm an acid. So again, don't let your logic fly out the window when you get really involved in the math, because I want things like those red flags to pop up and make you rethink, because hopefully you rethink and you go, oh, that 2.04, that's actually my pOH, which means you just have to do this really simple calculation to then get your pH. Okay, all right, so let's keep going because I don't see any questions. We've done a weak acid. We have done a weak base. How are we doing on time? We're doing okay on time. Okay, so now we're going to do neutralization. So there are two problems that I hope to get through, but I don't know if we will because they're going to take a while. I want to do a titration of a strong acid and a strong base, and I want to do a titration of a weak acid and a strong base. And I don't just want to do one calculation with this, I want to do a couple calculations. So let me just read this problem. A student is preparing to do a titration with hydrochloric acid and sodium hydroxide. She is using a 50 milliliter sample of a 0.25 molar solution of hydrochloric acid. Her solution of sodium hydroxide is 0.3 molar. What is the equivalence point of this titration? What is the pH of the solution at the equivalence point? And then calculate the pH of the solution 10 milliliters before the equivalence point and then 10 milliliters after the equivalence point. So what this is basically, well, I think of it as three different calculations. A calculation at the equivalence point, a calculation before the equivalence point, and a calculation after the equivalence point. Okay, so a couple of things. A titration is just a neutralization, a titration does not have to be between an acid and a base, but basically you've got an analyte and you're dripping in titrant. It's very commonly used with acids and bases, so we have a neutralization reaction here. Also, equivalence point is what you find mathematically using your stoichiometry. If you are doing a titration in lab and you are using an indicator, you are actually finding an end point, which is where the color change occurs, and that should be close to the equivalence point, but it's not quite the same thing. Okay, so with that being said, let's make sure there are no questions on that. It's all about the language, the chemistry language. Let's go ahead and calculate first what the equivalence point is of this titration. So the first thing I want to do is I want to write a balanced chemical equation. What is going on with this acid reacting with this base? So I have hydrochloric acid plus sodium hydroxide. I mean, this is like the classic neutralization reaction, right? Okay, so when you have an acid reacting with a base, again, especially a strong acid reacting with a strong base, you are going to form a salt, and specifically you're forming a salt from the anion from the acid and the cation from the base. So our salt is sodium chloride or table salt, and then you form water, because after you take let's do yellow. After you take out the chloride and the sodium, what's left? One hydrogen and a hydroxide, hydrogen hydroxide, bam, water. You can also think of these as double replacement reactions. That works out the same way, but an acid plus a base gives you a salt plus water. Okay, now the nice thing about this reaction is, again, if you look at the stoichiometry here, it's all 1-to-1. This is really going to help us with our math in this problem. It's just going to simplify the math a lot. You don't always get this, but you've got a monoprotic acid reacted with a strong base, so you've got a 1-to-1 ratio. Now, if we're going to do stoichiometry, which we need to do to find the equivalence point, the unit we always need to be in is moles. So I have a volume and a concentration for hydrochloric acid, and I have just a concentration for my sodium hydroxide, which means I can find moles for my acid, but I can't find moles for my base. So sometimes it's helpful to kind of pick apart what you have, what you know, and what you can find, because I know some students get really stuck because they know they can't find moles of the base and they're trying to focus on that. But I want you to focus on what you can do. You can find moles of your acid, so let's do that first. So we have 0.25 molar. So I am going to write this just to show a little bit different way. Remember, molarity is moles over liters of solution. So a 0.25 molar solution is 0.25 moles of hydrochloric acid over 1 liter of solution. What's nice about writing it like this is it can then be used as a conversion factor. So you don't have to write it with moles on top and liters on the bottom. If you use it as a conversion factor, you can actually flip it. I'll try to work one of those calculations in. Okay, so that is my concentration of hydrochloric acid. I have my volume. I got to be careful though. Molarity is liters of solution. I have milliliters here. Again, this is a really easy conversion. You're just going to move that decimal point 3 places to the left. You're just dividing by 1,000. But I do want to make sure that my units match up. So this becomes 0.50 liters of solution. Again, this is where hopefully red flags would be going off, because I hope that you guys are always, when you're doing any kind of math, that you're always writing down your units. And if you kept this at milliliters, you'd see that your liters of solution don't cancel. But when you convert to liters, everything cancels and works out. Okay, so this is going to leave us with moles of hydrochloric acid. We have 0.0125 moles of hydrochloric acid. At the equivalence point, what is special about the equivalence point? Well, at the equivalence point, you have the same number of moles of acid as the same number of moles of base. So when you think about what's going on, like if you're in the lab and you're doing this physically, you've got this 50 milliliter sample, probably in an Erlenmeyer flask. You know the concentration, and you are literally dripping in sodium hydroxide. So what we're really up for is we want to know what volume of sodium hydroxide we need to add to neutralize all of these moles of acid. So we want to react it completely and exactly. So we don't want excess moles of acid left over. We don't want excess moles of base left over. We want it to be exactly the same. Okay, so that means I need to convert this moles of hydrochloric acid into moles of sodium hydroxide. This is where having the 1-to-1 ratio is just, it's so nice. I love the 1-to-1 ratios. Okay, so this is our stoichiometry. I'm taking my moles of hydrochloric acid, and I have a 1-to-1 ratio of hydrochloric acid to sodium hydroxide. This is also why whenever you're doing a problem with a chemical reaction, make sure you write down the balanced chemical equation. Okay, there's no math involved here, excuse me. Sorry. Okay, we need the exact same number of moles of sodium hydroxide that we have of hydrochloric acid, because it's a 1-to-1 ratio, which means after you spend some time doing these problems, this is a step that you maybe don't need to explicitly write down. But again, when you're starting out, make sure you write down all these steps so you know where you are. Okay, now I know how many moles of sodium hydroxide. I have a concentration. I can figure out how many milliliters of sodium hydroxide I need to drip into my sample to reach that equivalence point. So taking my moles of sodium hydroxide. Okay, I'm going to use my concentration as a conversion factor here. So my concentration is 0.30 molar. So I can write this concentration as a conversion factor. So you can see it's still molarity. It's still moles over liters. I've just inverted it. Now, if this is not comfortable for you, just plug into your equation for molarity. You'll get the exact same thing. Again, this is where you have multiple avenues to get the same answer. Choose the way that you're most comfortable with. Choose the way that makes the most sense to you. Okay, so going back to this calculation, I did do this calculation, and this is going to, whoops, let me show this. My moles of sodium hydroxide cancel, so this is going to give me my liters of sodium hydroxide, and it is 0.0417. Again, that is liters of sodium hydroxide, but sometimes this makes more sense in milliliters, although the problem didn't specify it. It's going to be easier if I have milliliters to know what is 10 milliliters before the equivalence point and 10 milliliters after the equivalence point. Okay, so that is a long time to answer what is the equivalence point of this titration. It is when you have added 41.7 milliliters of sodium hydroxide. Okay, on to the second one. What is the pH of the solution at the equivalence point? Okay, again, let's think about our balanced chemical reaction, which we have right up here. Remember, at the equivalence point, I've added just enough base that I have used up all of my hydrochloric acid, and I also have no more sodium hydroxide. This is a limiting reagent reaction, but this is a limiting reagent reaction where you have exactly used up all of your reactants. Okay, so what is left in solution? Sodium chloride and water. All right, so let's think about sodium chloride. Are there any acid-base properties in sodium chloride? No, sodium chloride has no acid-base properties. Again, this is table salt. You can add table salt to a solution and you can change up concentration of table salt. You can change up ionic strength, but you're not going to change the pH of the solution. So what drives the pH of the solution at the equivalence point for a strong acid and a strong base? Water. Can water act as an acid? Yes. Can water act as a base? Yes. So what is our acid-base reaction if we have a solution with a salt that doesn't change pH at all and water? It's the autoionization of water. This is our acid-base reaction. So what is our equilibrium here? This is just our Kw. We have pure water. So I don't even have to do any calculations. What is the pH of pure water? pH equals 7. How do I get 7? Remember, Kw is 1 times 10 to the negative 14th. What does that mean for our concentration of hydronium? It means it's 1 times 10 to the negative 7th. So if I do my pH equals negative log of 1 times 10 to the negative 7th, guess what? I get a pH, of 7. This is why pure water has a pH of 7. It doesn't just magically appear. It actually has a basis in the equilibrium concentrations of hydronium and hydroxide of pure water. Okay, all right. Oh, hi, Jessica. I'm glad you could join us. Well, let me think, where are we? So what is the pH of the solution at the equivalence point? The pH is 7 because we have a salt which doesn't have any acid-base properties, and our pH is dominated by water, which means our pH is 7. Let's go ahead and we'll tackle this guy. Calculate the pH of the solution 10 milliliters before the equivalence point. Okay, so our equivalence point is at 41.7 milliliters. What was the pH 10 milliliters before we reach that point? Okay, so that means I need to know, and I think I have another page here. Yes, I need to know the pH at 31.7 milliliters of sodium hydroxide. All right, so this is what I'm after. What I want to know first, okay, so I know my moles of hydrochloric acid, right? That was in my sample. I just calculated that right here. So once I've added 31.7 milliliters of sodium hydroxide, how many moles have I added? Because I'm going to need to do some stoichiometry. So we've got, again, our concentration of sodium hydroxide. I'm going to write it as a conversion factor so I can get to my moles of sodium hydroxide. So again, I've added 31.7 milliliters, change it into liters, 3 places to the left. 0.0317 liters of sodium hydroxide. Again, making sure that units cancel always, liters. So at this point, 10 milliliters before I have reached the equivalence point, I have not added very many moles of sodium hydroxide, but that's how many moles of sodium hydroxide that I have added. All right, so remembering again from our previous problem, this is how many moles of hydrochloric acid I have started with. This is my sample. So I have 0.0125 moles of hydrochloric acid. Writing down, let's definitely get our balanced chemical equation written on this page. Okay, remember we're making sodium chloride plus water. I have a limiting reactant or a limiting reagent problem here, but this is going to be an easy one, I promise. I I know that I have added my 0.00951 moles, but I started with 0.0125. Remember, what is the stoichiometric ratio here? It is a 1-to-1 ratio. That means, let me just go ahead and show this. If I have this many moles of sodium hydroxide, when I convert this into moles of hydrochloric acid, again, you can see that units cancel. That means that I have used, oops, I'm losing track of my zeros. Moles of HCl have been used, or you can think of this as moles of hydrochloric acid have been reacted. So when I'm doing this reaction, first I have to identify my limiting reactant. Well, this is easy because we know we're before the equivalence point. We have not added enough sodium hydroxide, right? So sodium hydroxide is my limiting reactant. I know how many moles of hydrochloric acid I have started with. I now know how many moles of hydrochloric acid I have used. So I can figure out how many moles of hydrochloric acid are still in solution. Okay, so let me go through that. This is what I have started with. I'm just going to rewrite it. Remember, this is my original sample of hydrochloric acid. I just calculated how many moles I used. That is 0.00951. Again, that is moles of hydrochloric acid used. I'm going to subtract these, right? Because what I start minus what I've used gives me how much I have right now. So we'll call this how many moles remain. That is 0.00299. Again, that's still moles of hydrochloric acid. So an interesting thing to note here with units, when you're doing subtraction or when you're doing addition, your units here must match, and that is your units that you have in the end. So it's unlike multiplication division where units cancel. You want to make sure your units match if you're doing addition subtraction. This is how many moles of hydrochloric acid I have left. I have no more sodium hydroxide left. That has all completely reacted. So what is going to dominate my pH at this point? Again, I have no base. My hydrochloric acid is going to dominate. Again, water, yes, does act as an acid, but it's a very weak acid. Hydrochloric acid is absolutely going to blow the doors off of water. Now, the great thing is, hydrochloric acid, this is a strong acid. When we put it in water, we get hydronium and we get chloride anion. Also, it's just a forward reaction, which means my concentration of hydrochloric acid is my concentration of hydronium. Okay, that's the great thing about having a strong acid. You only have the forward reaction. We don't have to do equilibrium. So I need to get my concentration of hydrochloric acid. Okay, I'm close. I've got my moles, but I need to divide that by my liters of solution. But this is where things can get a little bit tricky. So my concentration of hydrochloric acid. Again, I have my moles right here. I just calculated that, 299 moles of HCl. Now I need to think about, I've got to divide by liters of solution. What are my liters of solution? Well, again, think about what you're physically doing in the lab. You started with your 50 milliliter sample, right? But we have been adding volume. We've been adding solution of sodium hydroxide. So we need to add that volume in because our volume has changed from what we started with. How much volume did we add? We added 31.7 milliliters. Okay, so you want to make sure that your volume here is what the volume you started with and how much you have added at this point. And my units here are not correct, are they? Those are milliliters. Those need to be changed to liters. So I am going to rewrite this. 299 moles of HCl. Eek. So when I add these milliliters and convert to liters, again, just move that decimal 3 places over, I get 0.0817 liters of solution. So now I have my concentration of hydrochloric acid, and that is 0.0366 molar, which means that is my concentration of hydronium because I have a strong acid. I need another page. I know you feel like when you're doing these calculations, like the calculations never end, but I promise they do end. Okay, so pH is negative log of hydronium. We just got that concentration. We got it right down here. So I'm going to do the negative log of this concentration, and I get a pH of 1.44. Does this make sense? Should we have an acidic pH at this point? Well, let's think about it. We've done a neutralization reaction here. What did we have left over? Did we have leftover acid, or did we have leftover base? Or was it like the equivalence point where we had just water? Well, remember, we haven't quite added enough sodium hydroxide. This was our limiting reagent. There is no more sodium hydroxide. There's a little bit of hydrochloric acid. So yes, it makes sense that we should have a pH that is low, that is less than 7, because, excuse me, we have an acid in solution. I'm not going to make it. I can't make it through all of these calculations. There are just so many calculations. Okay, so let me pose this question to you, because of course we haven't even finished this question yet. So this was the pH of the solution before the equivalence point, and we haven't done 10 milliliters yet after the equivalence point. Let me just talk through this really quickly, and then I'll actually show you my other problem that I was going to work. So after the equivalence point, again, we're still doing this neutralization reaction. After the equivalence point, it means that we have no more hydrochloric acid. Our pH is going to be dominated by our sodium hydroxide. So we have just a strong base in solution. This is another situation where, just like you saw with the ammonia, you're going to end up calculating pOH first and then pH. So always be careful with that. Make sure you know if you're dealing with an acid or a base, and are you dealing with hydronium or are you dealing with hydroxide? Again, it makes it easy that this is a strong base in solution, because once you get your concentration of sodium hydroxide, that equals your concentration of hydroxide, which means you've got a really, simple situation like this, where you can easily get your concentration of hydroxide. Before I end this live stream, because I know it is 8 o'clock, I did want to at least show you this problem here. So what we've got here is, I'll just read it out. What is the pH of a 15 milliliter aliquot of 0.2 molar nitric acid? What is the pH after 5 milliliters of 0.3 molar potassium hydroxide is added? What is the pH after 5 milliliters more potassium hydroxide is added? And what is the pH after 5 milliliters more potassium hydroxide has been added? So you're looking at what is the pH before you start the titration and you just have your weak acid. What is the pH after you've added 5 milliliters? What is the pH after you've added 10 milliliters? And then what is the pH after you've added 15 milliliters? And kind of spoiler alert, this is after 5 milliliters, you haven't reached the equivalence point. At 10 milliliters, you've reached the equivalence point. And then, of course, at 15 milliliters, you're past the equivalence point. And you can see the pH change according to that. The wrinkle in this one, which makes it quite a long problem, is you have a weak acid, which means you need to take into account equilibrium. Now, I am happy to do this problem if you guys want to see it next week on the live stream. If you're interested just in knowing what the answers are, just leave a comment. You can either comment now, or you can leave a comment in the comment section, and I'm happy to post the answers if you want to work through these problems Oh, sorry, I saw this one question. Will this full stream be posted later? Yes. So this full stream will immediately go up on the channel. It'll be under the live stream, so you're more than welcome to watch it whenever you want. But again, if you want to know the answers to these problems, I'm happy to go ahead and post those. Just let me know what's going to be most helpful to you guys. I didn't think I was going to make it through all the problems today. I really wanted to, but it just takes time to work through all of the math of these problems. But again, this is one reason why I know acids and bases are difficult, especially when you're dealing with, again, like this problem here where you've got a strong base and a weak acid. It just can make it really tough because then you've got to deal with equilibrium on top of it. So anyway, thanks to everyone who joined me today. I will hopefully see you next week. Let me know what you would like to see, and I'm happy to work through any kind of calculations. Thanks so much. Bye.